Hello everyone and welcome to this tutorial on information design in operations. My name is Ozan Candogan and I'm a faculty member at the University of Chicago's Booth School of Business. Today I'm excited to tell you about information design and its applications in different operational settings. So for those of you who do not know, information design has been a fast-growing area in economics in the last decade or so, and there have been many beautiful fundamental contributions to the literature recently. And in operations, in the last few years, we have seen many applications of information design as well. And in fact, just this informs, I am participating in 3 different sessions that are titled Information Design in Operations. And this suggests that this is a growing area in operations as well. And my objective in this tutorial is twofold. On one hand, I would like to tell you about basics of information design, what information design is about, and what are the approaches that have been developed in the literature when it comes to designing optimal information structures. So I would like to cover some fundamental papers that address these questions in the first part of my talk. Second, I will focus on different applications of information design in different operational contexts, and I would like to present, without going too much into the details, I would like to highlight few works from the recent literature that apply tools and ideas from information design in different operational contexts. My hope is that at the end of this tutorial, some of you will find the area interesting and will decide to learn more about it, and hopefully in future Informs conferences you'll contribute more talks related to this topic. So with that, let me get started, and let me start with a simple example. This example is adapted from the seminal paper of Kamenicker and Gansko. In that paper they have a famous prosecutor example, and I adapted that example to think about the interaction between a firm and a buyer. So here's the setup. The firm faces a buyer, and the firm is offering a product whose match with the buyer is a priori unknown. The firm and the buyer, on the other hand, share a common prior, and they agree that the match will be of good. The match between the product and the buyer will be good with probability 0.3, and not good with probability 0.7. The crucial thing which makes the interaction between the firm and the buyer interesting is the following. Their incentives are misaligned. The firm just cares about selling the product and has a payoff of 1 unit if the product is sold to the buyer and 0 otherwise. The buyer, on the other hand, wants to purchase the product if the quality is good, and she wants to not purchase the product if the quality is bad. So buyer has a payoff of 1 from taking the correct action. In other outcomes, if the product is of poor quality and the buyer purchases, or if the product is of good quality and the buyer does not purchase, the payoff is normalized to 0. Now, the question is, can the firm somehow persuade the buyer to go ahead and purchase the product? And to that end, we'll think about the following. We'll think about a firm who can commit to a mechanism that reveals informative signals about the product. So what do I mean by this? Well, for instance, you can think about something like limited trials. So we give the product or a version of the product with some limited capabilities to the buyer. We ask the buyer to explore this product for a duration of a limited trial and decide whether the product is a good match for her or not. Importantly, the firm designs the trial, right? The firm decides on what type of signals might be revealed to the buyer. Let's think about some signals that might be relevant. First, the boring signal, if you will, the uninformative one. So the firm does not provide any trials or any information to the buyer. In that case, think about the decision problem of the buyer. The buyer knows that the match is good with probability 0.3 and bad with probability 0.7. So the expected payoff from not buying is 0.7, expected payoff from buying is 0.3. The buyer decides not to buy. So the firm's payoff without any information revelation is going to be equal to 0. Let's say that the firm does goes to the other extreme and gives the product to the buyer for an extensive period of time with all the capabilities, so the buyer can explore the product in depth and truly learn whether the quality is, whether the match is good or not. Well, in this extreme where we fully reveal the state, the buyer adopts only when she is convinced that the match is good, which happens with probability 0.3. So the expected payoff of the firm in this case is 0.3 units. The key question is, can we do better? And information design tries to answer this question, and the answer is yes. So here's what the optimal information structure looks like for this example. Suppose that the firm adopts a mechanism, a trial, which reveals the state fully when it is good, and when the state is not good, when the match is of poor quality, then the mechanism reveals randomized signals, which suggests that the match is match is good with probability 3/7 and bad with probability 4/7. Note that in this setting, the buyer observes the bad signal only when the quality or the match is indeed bad, and the randomization device suggests that the match is bad, which happens with probability 4/7, conditional on the match being of low quality. Now think about this from the point of view of the Bayesian buyer. This buyer, if she sees that the signal is bad, she can infer that for sure we are in the bad state, because that's the only state where the buyer even gets to observe the bad signal. If the signal is good, on the other hand, the buyer can't tell for sure whether the match is good or bad. This is because the buyer receives the good signal when the state is good, but she also receives the good signal when the state is bad. In that case, conditional on the state being bad, the buyer still receives the good signal with probability 3/7. And you will immediately see that the total probability of the first event is 0.3, and same with the second event. So from the point of view of the Bayesian buyer, after observing the good signal, she'll conclude that both states are equally likely, which means that the buyer is indifferent between purchasing and not purchasing. In that case, we break ties in favor of the action that yields a higher payoff to the designer, and we conclude that the buyer purchases the product. So the important point to take away is that in this setting, under this mechanism, the buyer does not purchase the product only in 40% of all the possible outcomes, or in other words, with 60% probability there is a sale, firm's expected payoff is 0.6. Revealing the information in this non-trivial way dominates not revealing any information at all and revealing full information. So indeed, we can do better. With the appropriate choice of the information structure, we can improve the designer's or the firm's payoff. Now, it is not too difficult to see in a simple example like this one, but the question is, how does this observation generalize in more interesting, richer settings? When is there room for information design? When can we benefit from choosing information structures appropriately? And that's what the information design literature focuses on. Here's the plan for the rest of the tutorial. First, I will focus on different approaches to information design, and I'll start here by focusing on the seminal paper of Kamenika and Candogan. In this paper, they introduced the concavification idea, which can be used to understand when a designer can choose an information structure in a way that strictly improves her payoff. So when is information design beneficial? It's a fundamental question, and the answer is provided through this concavification idea, which I'm going to discuss with you. Second, I will briefly focus on the contribution of Bergman and Morris. Here, they relate the information design question or persuasion question to the concept of correlated equilibrium from game theory. This connection is nice, but it also allows us to formulate the question of designing optimal information structures through a simple linear program. Now, the downside is that this linear program is very high dimensional possibly, and it's not always possible to solve it and determine what optimal information structures look like. And in addition, it may not be always possible to say something structurally interesting about the optimal information structures through the solution of this linear program. I'll then talk briefly about my recent work in this area, where I propose a convex programming framework that can be used to characterize optimal information structures in a tractable way in settings where the state belongs to a continuum and where the receiver or receivers, agent or agents, care only about the posterior mean that's induced by the signals of the designer. Then I'll switch gears and I'll start talking about applications in different operational settings. And I'll start here by the application of information design or persuasion in network systems. In some recent work, I've focused on how information can be used as a lever to induce desired outcome in different networked environments. And here it turns out that we can leverage the ideas that I just mentioned, the convex programming framework that I just mentioned, for the characterization of the optimal information structure. And I'm going to comment on that in the second half of the tutorial. Kimon Drakopoulos and others have written a real nice recent paper that is about signaling product availability. They think about a setting where a firm is experiencing some uncertainty about the available inventory, and the firm can send informative signals about the inventory availability or the stock out risk to the buyers in a way that maybe persuades them to purchase early at a higher price. So this is a neat application of the information design ideas to a almost classical revenue management setting, and I will briefly talk about that. Ramesh Johari, Barlight, and Gabriel Weintraub have a real nice recent paper that focuses on designing optimal information structures in two-sided markets. That will be the third application I will focus on in the context of operations. After these applications, I will briefly conclude and highlight some future directions as well as some recent and ongoing work in the area. Before I proceed any further, I should mention that there are many other beautiful papers in the literature. There are papers that focus on various foundational issues as well as various interesting applications. Unfortunately, I don't have time to go to the details of all of these, but I'm hoping that at least some of you will go back to the tutorial paper that I wrote that complements the talk today, and these papers are cited there. Hopefully, we'll check out some of these papers. On the side of foundational questions, there are many interesting information design settings that the recent literature has explored. There are papers that focus on settings where the receiver has some private information. There are papers that focus on settings where there are informational spillovers among many receivers. There are papers that focus on designing robust information structures. And unfortunately, I don't have time to go to details of any of these, but I think there are many interesting developments in the area, and you'll see that many of these papers are actually quite recent. There are also very challenging, interesting algorithmic questions when it comes to designing optimal information structures, and I think there's more work to be done in this area as well. In the context of operations, Chris Iyer has quite a few interesting papers related to applications of information design in different queuing systems. If you're interested in queuing and if information design sounds interesting, I highly recommend that you check these papers out. Chris Iyer also has some applications of information design to revenue management settings. I already mentioned Kimo's paper, and we are going to discuss it in more detail. But in addition, there are other papers. For instance, Can Küçükgöl, Özal Pözar, and others have a really nice recent paper related to application of information design to different revenue management settings. You may want to check out that paper as well. In many platforms, information is a natural lever, and we are seeing more and more applications of information design ideas in different platform settings. Some of Yangos Papanastasios' earlier work may be related to this. I already mentioned the paper by Ramesh Johari and others, which I'm going to detail later on. Kostas Pimpikis has some other recent work related to information in platforms, and Yang, together with Chris Iyer and Peter Fraser, has a paper that focuses on applications of information design to spatial resource competition, which might be relevant for instance, platforms like Uber and Lyft, where there is a natural spatial aspect to the application and operation of the platform. And these are some of the nice applications that I have noticed in the literature, and I suspect that there will be many more. Again, unfortunately, I won't go to the details of this, but I'm hoping that you'll check out the relevant papers. With that, let me dive right in. I'm going to next talk about different approaches to information design, and then I'll discuss some applications in operations after that, and after that I'll conclude. Okay, let me go to the details and describe the basics of the information design setup. We are going to assume that there's an underlying state of the world, which is denoted by T. We are going to model the state by a random variable. A priori, the state is not known by the receiver or the designer or the sender. And we are going to assume that the state is distributed according to a known distribution, which I denote by F. We are going to assume that, for now, we are going to assume that there is a single receiver, and the receiver decides what action to take. If she takes action little a, which belongs to the set of possible actions capital A, her payoff, the receiver's payoff, is given by U, A, T, where T is the state realization. So this is important. The payoff of the receiver depends on the action as well as the underlying state, the realization of the underlying state. The designer's payoff similarly depends on the action as well as the state, and I'm going to denote the payoff of the designer by nu. I'm going to make the following assumption for now. The set of possible state realizations, script T, is finite, and the set of actions is compact. So A is compact. So this finiteness assumption is not needed for some of the results that we are going to discuss in a bit. And at some point, in fact, I'm going to explicitly relax that assumption. But for now, I'm keeping it because it is conceptually simpler to think about settings where the set of states is finite. And at the same time, it simplifies the notation a little bit. So I'll stick to this assumption for now. Here's the important part. A priori, the receiver and the designer are uninformed about the state. They do not know the state. They both just know the distribution of the state. The designer commits to a mechanism, which I'm going to note by pi, which maps each state realization, possibly after randomization, to a signal realization. So choosing the mechanism or choosing the signal is really the same thing as deciding what signal to send, what signal realization to send to the receiver for each state. And you can also say that if state realization is something, I'm going to randomly pick one of these signals and send it to the receiver. That's also allowed. In fact, in the example that we discussed in the beginning, such a mechanism was the optimal mechanism. Now, here I highlighted the word commits, and this is important. There's an important commitment assumption here. And this assumption says the following: the designer chooses her mechanism, commits to it before the state is realized, knowing only the distribution of the state, not the realization, but just the distribution of the state. Then once the state is realized, the designer sends signals to the receiver consistently with the mechanism that she committed to. So what we are disallowing is the following: the designer observes the state, and if the state is bad, or if the state will trigger a signal that leads to an undesirable outcome for the designer, she deviates and decides to send a completely different signal. That's not allowed. Okay, so commitment says that before the state is realized, you choose your mechanism, you choose what signals to send for which state realizations, and again, randomization is allowed. And once the state is realized, signal is produced in a way that's consistent with the mechanism that the designer committed to. So this is an assumption, and we'll comment more on that assumption. This is an important assumption. What are some examples of mechanisms? What are some examples of these mappings from the states to possible signal realizations? Well, we already have seen a few. Let's go over them quickly. The first example is just the full revelation mechanism, right? I can commit to a mechanism where the signal is equal to the state, where the signal exactly reveals what the state realization is. So the designer can commit to such a mechanism, and when the state is realized, the designer can go ahead and share the realization of the state exactly with the receiver. So that's allowed. Another example is the uninformative mechanism, which again was a benchmark that we discussed in our first example. If I'm always sending the same signal, regardless of what the state is, my signal is not informative about the state. So in that sense, it's an uninformative signal. That's also allowed. I can do something more interesting. I can, for instance, focus on a threshold signal. This is relevant when the state is a real number. I can pick a threshold alpha, and I can reveal whether the realization of the state is above my threshold or below that threshold. So you can think about the higher states as good states, lower states as bad states, and the designer can choose a threshold and help the receiver learn when the state is good versus bad, right? That's an example of a mechanism. The designer can commit to this alpha, and given that alpha that she committed to, once the state is realized, she can reveal she can evaluate this indicator variable and reveal it to the receiver. Receiver does not learn in this case exactly what the state is, but she can learn whether it is below or above alpha. Or you can do some randomization, similar to what we saw in the earlier example. In that example, when the state was good, the signal was good. When the state was bad, the signal was good with some probability and bad with the complementary probability. That's also allowed. What about the design problem of the information designer? Well, before I can state to you the design problem, let's focus on how the receiver behaves given a mechanism or given the signal associated with a mechanism. Well, if the receiver does not observe a signal, or if she does not know anything about the underlying state, she basically takes an action that would maximize her expected payoff using the distribution of the state. But if you observe a payoff-relevant signal, you update your posterior about the state, and then go ahead and take the corresponding action. So in a way, by choosing the information structure appropriately, the designer can influence the actions that the receiver will take. For a given mechanism, or equally for a given signal, the receiver's problem is simple. She decides what action to take for each signal realization. If there are multiple actions that are maximizing her payoff, if there are multiple strategies that maximize her payoff, we are always going to assume that the receiver breaks ties in favor of the action that yields a higher payoff to the designer. So it's a tie-breaking assumption. In the information literature, you will see that the papers often talk about the sender-preferred equilibrium, and it basically refers to this tie-breaking assumption. If there are multiple outcomes that can emerge for a given mechanism, focus on the one that yields a higher payoff to the designer. What is the designer's problem? Well, when I choose my mechanism, I am basically committing to different possible signals. And these signals at the end of the day influence the action that the receiver takes and therefore the payoff of the designer. Designer chooses the mechanism pi in the first place so that the induced expected payoff is maximized. That's also what we saw in the initial example. We talked about the designer using the full revelation mechanism, uninformative mechanism, or a randomized mechanism, and we saw that by appropriately choosing the mechanism through appropriate randomization, she can guarantee a higher payoff. So more broadly, for any given payoff structure for the receiver as well as the designer, how can the designer choose her mechanism so that the induced expected payoff is maximized? That is the designer's decision problem. So far, I've been focusing on a setting where there's a single receiver. The idea is immediately generalized to settings where there are multiple receivers as well. In a setting where you have multiple receivers, when you fix the mechanism, it basically induces a game of incomplete information among the receivers, where receivers have access to some state-related signals. Let's say that the outcome of this, let's focus on the solution concept that would allow us to characterize the outcome of this interaction among the receivers. At the end of this game, we can determine the outcome by focusing on the corresponding Bayes-Nash equilibria. Let me denote by Q the set of all Bayes-Nash equilibria that is induced for a given mechanism pi. I'm going to again I'm again going to make the standard preferredness assumption. That is, if there are multiple equilibria, I am going to focus on the best one. Best one meaning the one that yields the highest payoff to the designer. The designer's decision problem then is the following. I will maximize over all possible mechanisms. I'll choose the one that yields the highest payoff to me, highest expected payoff to me at the end of the day, given the actions of the receivers. More formally, a given mechanism pi induces many Bayes-Nash equilibria. If so, I will focus on the best one and evaluate my expected payoff. That's the payoff that I can guarantee under mechanism pi. Optimize over all pi, optimize over all mechanisms, and achieve the one that maximizes the expected payoff that the designer can guarantee. So this is the decision problem of the information designer. Let's go back to the commitment assumption. I already mentioned that it's an important assumption which might be hard to justify in practice. In a way, this assumption is similar to the commitment assumption in mechanism design. Think about, for instance, an auction design setting. The designer decides on the rules of the game. Given the bids, how is the allocation decided on, how is the allocation determined, what are the payments, and so on and so forth. I choose these before the bids are reported to the designer, and once the bids are reported, I just allocate the good and charge the payments according to the rules that I committed to. I do not change the rules of the game once the bids are observed. This assumption, the commitment assumption in information design, is also similar. The designer commits to the mechanism before the state is realized. Once the state is realized, she shares signals with the agents in a way that's consistent with the mechanism that the designer committed to. How can this assumption be justified? Well, in some settings, it is natural. Think about the product trial example that we discussed earlier. The designer chooses what, let's say, features of the product can be explored by the agent. The designer commits to the structure of the trial. Once the designer chooses that, it is up to the agent to decide whether the fit is good or not. The designer cannot adjust the features to be tried depending on the realization of the state, depending on the fit between the possible buyer and the product. That's not allowed. I commit to the structure ex ante before even the trial begins. There are other settings where this assumption can be enforceable. The prosecutor example of the seminal paper of Kamenika and Gansko is an example, and you may want to check out the relevant discussion there. There are some other settings where reputation effects can be used to justify commitments, formally or informally. You can think, for instance, about a platform who sends informative signals about the quality of a product to the possible buyers, to the receivers. And you can think about the platform using a certain, let's say, star rating or buy, do not buy type of recommendation. And the platform chooses this mechanism and reveals signals to the users. But let's suppose that the platform deviates from the chosen mechanism and starts sending the buy signal or the 5-star rating even for low-quality products. Well, if something like that were to happen, the buyers would possibly stop working with this platform. The reputation of the platform would be harmed, and in the long run, the platform may suffer from that. So because of that, a platform may not want to change the way that the signals are generated in a way that the ratings are displayed in a way that maximizes its sales, in a way that that changes once the state is realized. So it is conceivable that some reputational effects, in other words, will force the platforms to stick to their information structure and not change it once the state is realized. And there are recent papers in the literature that actually argue formally that this can be the case in some settings. If you have a designer who is interacting in the long run with many receivers, because of some reputational concerns, the outcome of the game induced between the designer and the receivers may be consistent with the outcome that you obtain, assuming commitment. So the reputational effects may, in a way, justify commitment. It is also important to notice that the commitment assumption and the optimal information structures that you obtain through it offer a natural benchmark. Right? Even if you do not have an information designer, even if you have a number of agents who are interacting with each other, maybe some of these agents have payoff-relevant signals, and depending on what type of signals are available to them, the outcome of the game, as well as the payoffs that will be induced at this outcome, may differ, may change. In such settings, you may want to have a benchmark which tells you what the best possible payoff would be if the agents were to have access to some additional information. Well, the information design benchmark that we are focusing on here under the commitment assumption gives such a benchmark. So I'm not going to dwell more on this, aside for just quickly reiterating the same point. Commitment is an important assumption. It requires some justification. In some cases, it is natural, and in some other settings, reputational effects can be used to justify it. And also, it is a natural benchmark. Even in settings where you may not be able to commit to an information structure and design information optimally, it may be valuable and interesting to know how the payoffs may differ based on some additional information the agents have access to. Now let's go back to the single receiver setting. What are the optimal mechanisms? We still haven't pinned them down. Well, it turns out that optimal mechanisms will always have a rather simple structure. Or I should say that there will always exist some optimal mechanisms that have a simple structure. Specifically, we can always restrict attention to the following class of mechanisms, where the realizations of the signals basically correspond to the different actions of the receiver, and sharing a signal or realization of that signal with the receiver can be just interpreted as recommending an action to the receiver. The recommendations are such that, given that signal realization, given that action recommendation, the receiver finds it optimal to follow that recommendation and take the corresponding action. In the information literature, such mechanisms are referred to as straightforward mechanisms. Basically, in these mechanisms, the designer commits to a recommendation scheme, which, once the state is realized, recommends an action to the receiver, and this scheme is such that it is incentive compatible for the receiver to follow the recommendation. The proof of the optimality of straightforward mechanisms, or the proof that it is without loss of optimality to restrict attention to this class of mechanisms, is also straightforward. This can be obtained through an application of the revelation principle. Specifically, suppose that I give you a mechanism that's not a straightforward mechanism, and in this mechanism, for some signal realizations, the receiver finds it optimal to take a certain action. Let me define another mechanism, which, when the original mechanism sends one of these signals, the new mechanism just sends a recommendation to take this action. In the new mechanism, the receiver will find it optimal to follow that recommendation, because this recommendation basically reveals that the signal of the original mechanism is in this set of signals which trigger the agent to take the corresponding action anyway. So if I directly reveal that to the agent, she will still find it optimal to take the corresponding action, which implies that I can start with any mechanism and construct the corresponding straightforward mechanism that is payoff equivalent. If that is the case, when I'm searching for the optimal mechanism, I can restrict attention to straightforward mechanisms without any loss. But there are still two questions. When should I bother? When does the sender benefit from persuasion or information design? And also, how can I obtain the optimal mechanisms? How can I obtain the best straightforward mechanism? These are still the questions that we need to answer. Let us answer this first question. First, fix a mechanism and think about the realization of the signal of that mechanism. Each signal realization induces a posterior belief, a distribution over the set of possible states. And when you fix a mechanism, you are basically fixing a set of possible signal realizations and the probabilities of each of these signal realizations. So effectively, you are fixing a distribution over these posterior beliefs, or you are fixing this function tau, which is a distribution over distributions. This function needs to satisfy some conditions. It needs to satisfy base plausibility condition, which basically says that when you take a probability weighted average of the induced posterior beliefs, you need to be consistent with the underlying state distribution F. Perhaps more importantly, for a given posterior belief mu, you can reason about the action that the receiver will find it optimal to take. Well, if you can reason about the receiver's action, you can also reason about the designer's expected payoff for the given posterior belief. And let me denote this by nu hat of mu. This nu hat function turns out to play a key role in the answer to this question about when persuasion is beneficial. Specifically, think about the nu hat function and its concave closure. A beautiful result due to Kamenika and Gensko establishes that if this concave closure evaluated at f, the state distribution, is strictly larger than nu hat evaluated at f, then the designer benefits from persuasion. Moreover, you can also reason about the optimal payoff of the designer when she finds the optimal information structure. That value is nothing more than the concave closure evaluated at the distribution f, at the initial state distribution, at the prior belief. This is a super nice result. It basically says that really the key object to think about is the payoff that the designer will receive under any posterior belief. And by comparing this nu hat function with its concave closure, you can reason about when there is value, when there is need for persuasion, when you can strictly improve your payoff by designing an information structure appropriately. Now, there are a couple of immediate corollaries as well. For instance, when this nu hat function is concave, its concave closure is itself, therefore, this gap is not strict, so you do not benefit at all from persuasion. When it is convex but not concave, then for almost every prior, you can see that you'll benefit from persuasion. So really, whether this nu hat is concave or convex is going to play a key role when it comes to deciding on whether there is room for information design, whether you can improve your payoff by choosing information structure appropriately or not. Furthermore, there's an important special setting, and this important special case is one where the designer's payoff only depends on the induced posterior mean. As opposed to the entire posterior distribution, mu, it depends only on the induced posterior mean, expectation of the state evaluated with respect to this distribution mu. Let me denote by nu tilde this function that maps the that expresses the designer's payoff as a function of the induced posterior mean. Well, concavification idea applies in this setting as well. So in particular, you can evaluate the concave closure of this function, nu tilde. Let me denote this by nu tilde sub c. If it is the case that nu tilde sub c is strictly greater than nu tilde when you evaluate these functions at the mean state, then designer benefits from persuasion. And this is an if and only if result as well. This is the concavification idea that is that you commonly see in practice. It's a beautiful idea. It teaches us when the designer benefits from persuasion. In some settings, you can characterize the concave closures of these functions nu hat or nu tilde in a straightforward way, for instance, when there are binary actions. And using this characterization of the concave closure, you can reason about the optimal mechanisms as well. But in richer settings, it may be infeasible to obtain the concave closure in a analytically tractable way. Still, in those settings, by solving a linear program, one can characterize the optimal information structures. Specifically, you would want to solve a linear program that looks like what I have on this slide. Here, my decision variable is sigma, and I'm assuming that there are finitely many actions and states. Sigma here is a function that is indexed with the actions as well as the state. And if there are finitely many actions and states, you can think about sigma as just a long vector, basically. How do I think about this setting? Suppose that for each state realization t, designer induces a distribution over possible outcomes, distribution over ai's and a minus i's. And this distribution that I am focusing on for each state realization t is exactly the quantity that you see over here. Now, here's a mechanism. For each state, the designer goes ahead and draws an action profile from this distribution sigma. And with each agent I, the designer shares the corresponding ai. Agent I does not know the state, nor does she know what actions are recommended to the remaining agents. Still, knowing this distribution sigma and the state distribution, here I'm denoting the PDF with little f, knowing these two, the agents can compute the expected payoff from taking action AI when she receives that recommendation to take action AI. This is the quantity on the left-hand side in the constraint. The quantity on the right-hand side basically says that, basically captures the payoff when the agent receives a recommendation to take action AI, but she deviates to some other action, A prime I. And the constraint just says that for the type of mechanism that I'm describing, each agent finds it optimal to follow her recommendation. And this is very similar to the idea of straightforwardness, right? I'm in a multi-agent setting here. I'm drawing an action profile for each state, and I'm choosing these draws in such a way that when I recommend each agent an action to take, she finds it optimal to follow that recommendation. The objective is the payoff that's induced for the designer when agents follow the recommendation that's made to them. By solving this optimization problem, by obtaining the optimal sigma, we can pin down the optimal mechanism of the information designer. It is without loss to focus on the class of mechanisms that I described to characterize the optimal information structure. But there's a drawback. This is a linear program, but it's a large linear program. Here, first of all, I forgot to mention, without the T indexing sigma, the object that you see here is closely related to the correlated equilibrium from game theory. Right? In a correlated equilibrium, you randomly draw a strategy profile, tell each agent the action associated with her in the strategy profile, and this distribution is such that each agent finds it optimal to take the recommended action. What you see here is very much like that, and it is just that for each state you are drawing, if you will, a different strategy profile. So because of this connection to correlated equilibrium in game theory, this object sigma here is sometimes referred to as the base correlated equilibrium, and the optimal solution here is the best base correlated equilibria that maximizes the payoff of the designer, which is our optimal information structure. Now, I said that there's a problem with trying to solve this LP directly, possibly, and it is the following. This is a large-scale LP. The number of decision variables increases with the number of states as well as the strategy profiles, which is exponential in the number of players. So that's a drawback, perhaps a computational drawback. It is also not necessarily easy to reason about the structure of the optimal mechanism through the solution of this LP. It's not clear what type of structural properties are associated with optimal mechanisms. Moreover, if you have a continuum of actions or states, it is not sufficient to solve a simple linear program. You are now looking at an infinite dimensional optimization problem, and obtaining additional structural properties may be even more difficult. Still, there are other important settings where one can obtain the optimal information structure following a tractable approach. And one such important setting is the one that I described in this slide. This is a setting where the payoff of the designer depends only on the posterior mean that her signal induces. Now let me describe an environment where this is indeed the case, and this is a fairly general environment. We have a finite set of receivers, and each receiver chooses her actions from a finite set. The payoff of each receiver depends on the actions that are chosen, as well as the state, but the dependence on the state is affine. Earlier, I made the assumption that the set of possible state realizations is finite. I'm going to relax that assumption. Here, I'm going to assume that the set of possible state realizations, script T, is a subinterval of the reals. So I may have a continuum of states. I will assume that the payoff of the designer depends only on the actions chosen by the receivers, not on the state, and the designer uses public signals. By that, what I mean is that the designer does not share a different signal or with each agent. The designer chooses only a single signal and shares its realization with all the receivers in the game. In this setting, it turns out that the payoff of the designer depends only on the posterior mean her signal induces. Moreover, this payoff is really a step function of the posterior mean that her public signal induces. And this is actually not too difficult to see. In the setting that I am describing, because of the dependence, affine dependence on the state, it should be clear that what matters is the induced posterior mean. As the posterior mean changes, the receivers start playing a game with a different set of payoffs. So the equilibrium outcome that emerges for different posterior means changes. We start at a low posterior mean level, let's say. For a while, the receivers play a certain strategy profile at equilibrium, and when the posterior mean is above a threshold, they switch to playing another strategy profile, and then they switch again, and switch again. And these switches basically induce a step function which can be used to express the payoff of the designer as a function of the induced posterior mean. So let's focus on this abstract setting. Let's say that the designer's payoff is a step function of the induced posterior mean, and let me parameterize this step function in terms of variables bk and rk. Rk is the reward associated with the kth step of my step function, and the endpoints of the kth step is between bk minus 1 and bk. So these bk variables characterize when the steps begin and end, and when the posterior mean is between bk minus 1 and bk, the reward associated with the kth step of the step function materializes, and the designer collects the reward of rk. Now, one needs to be a little bit careful about the endpoints of these steps. One needs to be careful about how the ties are broken, and I'm going to break the ties in a way that is more favorable to the designer. In general, the steps can be left or right closed, and it depends on the tie breaking that I'm mentioning here. I won't be precise about that in this talk. Okay, so just keep in mind that some additional care may be needed at the endpoints of the steps. Now, think about the setting that I described, where the designer's payoffs can be expressed as a step function of the induced posterior mean, which captures this as a special case. What are the optimal information structures in this case? It turns out that this can be characterized in a straightforward way. The first step towards establishing such a result and characterizing the optimal information structures is this result. This result says that one can restrict attention without loss of generality. One can restrict attention to a set of public signaling mechanisms where the signal realizations correspond to the different steps of the underlying step function. And when the signal realization is k, then the induced posterior mean will be in the interval associated with the kth step of the step function between bk minus 1 and bk. This result is very similar to the straightforwardness result that we discussed earlier, and I'm not going to detail that, but it is a structural property of the signals. It's a special class of signals that you can restrict attention to without loss of optimality. Now, we are still going to figure out, we still need to figure out how to search over this class of signals, how to search over signals that belong to this class in a way that maximizes the designer's payoff. A priori, it's not clear. To make progress in this direction, here's what I'm going to do. Fix a signal S that satisfies these properties, and let me associate some quantities with the signal S. Pk will be the probability with which the realization of the signal is equal to k, and zk is the expectation of the state times the indicator variable that the signal is equal to k. Also equivalently, zk over pk is the posterior mean that's induced when the signal realization is k. The pk-zk tuple for a given signal S will be referred to as the consistent pk-zk tuple. So this tuple is consistent with the signal S. Now, the high-level idea is the following. We do not know how to search over the optimal signals that satisfy these properties directly. We can search over the pz tuples that are consistent with some signal S. Let me denote the set of such consistent tuples with T. We will search over these tuples, and then we are going to reverse engineer a signal that is consistent with the optimal tuple. In more detail, here's an optimization problem that we are going to solve. Here the constraints that I have are non-trivial. They depend on the underlying state distribution, and these constraints basically are a relaxation of the constraint that the pz tuple is consistent with some signal. I'm not going to detail this here. I'm happy to describe it in more detail later on. And these constraints are not trivial. But basically, these are the constraints that are satisfied by pz tuples that are consistent with some signal. So I'm going to impose these constraints, and my objective is to maximize the expected payoff. Remember, pk basically captures the probability with which I send signal k. When I send signal k, the posterior mean is in the interval bk minus 1 to bk, and I collect the reward of rk. So this is my expected reward. So I'll search over the pz tuples that satisfy the consistency requirements, or rather a relaxation of it, and I'll find the tuple that maximizes my expected payoff. In the second step, I'm going to construct a public signal that is consistent with the optimal tuple p star z star. It's not obvious that you can always do that, because as I mentioned earlier, these constraints are really relaxation of the constraint that I needed, but it turns out that this is a tight relaxation. Given the optimal solution, you can always construct a corresponding consistent public signal. It is not clear at all how to do that algorithmically. It turns out that there is a simple recursive algorithm, there is a tractable algorithm that allows for constructing the optimal signal. And it turns out that the optimal signal always has a simple structure, which I refer to as a double interval structure. So in this picture, I'm trying to illustrate what I mean by the double interval structure. Optimal signal basically takes the set of possible state realizations, which is the horizontal bar here, and partitions that. Here, I'm thinking about a setting where my step function has, let's say, 4 different levels, and when I partition the set of state realizations, I have 4 different colors, 1 color corresponding to each step of my step function. So when the state is in the blue interval, I publicly send signal k, if blue is the color associated with the kth step of the step function. This induces a posterior mean associated with the kth step of the step function and a reward of rk. The name double interval is coming from the fact that with each step of the step function, with each possible signal realization, I associate at most 2 subintervals of the states. So it could be the case that the optimal information structure is such that with some step L, I associate the green color, I associate 2 different intervals. When the state is in, when the realization of the state is in this interval or that interval, I do not exactly tell the receivers what the agents what the state is. I just tell them that the state belongs either to this interval or to that interval. And this defines a signaling mechanism, and optimal signaling mechanism basically always relies on such double interval partitions. How to construct these mechanisms? Well, solving this convex optimization problem and following the recursive algorithm that I have in the paper, one can actually explicitly, in a tractable way, characterize these intervals and the optimal public signaling mechanism. So let's focus on some applications of information design in operations, and along the way we are going to leverage some of the ideas that we just discussed. The first application comes from a recent paper of mine where I focus on persuasion networks. Operations community has done a lot of interesting work related to understanding how one can use the available social network information for better, let's say, targeted pricing decisions. And at a high level, these papers focus on understanding how we can use transfers through prices to induce a desired outcome at the end of a network game. Well, information is an equally important level and perhaps a more natural lever to induce a desired outcome at the end of the interaction in social networks. And this paper provides a framework to thinking about how to use information as a lever in networks. So here is the setting that I am going to focus on. We have an underlying social network. Nodes correspond to the agents in this network. And let's assume that the network is unweighted and GIJs capture the entries of the adjacency matrix. They are zeros or ones. Agents take a binary action, 0 or 1. Think about product adoption decisions. Agents either take action 0. If an agent takes action 0, her payoff is 0. Or the agent takes action 1, in which case her payoff depends on the state, underlying state, which is, let's say, the quality of the product, plus a network externality term. If more of my neighbors in the network adopt the product, I will be inclined to adopt the product as well. So this second term that you see in the payoff here is the network externality term. The designer's objective is to maximize the total number of agents who take action 1. And the designer restricts attention to using public signaling mechanisms. And the question is, what is the best public signaling mechanism that ensures that the total number of agents who adopt the product will be maximized? So this is the key question. Now, given that I'm looking at public signaling mechanisms and given that agent's payoff is state plus a network externality term, you would notice that we are in the environment that I described earlier. In this setting, the only quantity that will matter for the designer's payoff will be the posterior mean of the state, like I described earlier. In more detail, think about fixing a mechanism and consider a signal realization, little s. This induces a posterior mean, and given that signals are public, all agents have the same posterior mean of the state. And given the signal realization, the agents in the network basically play a game with the payoffs that are given here. This is a supermodular game. It has the largest equilibrium and the smallest equilibrium. When we focus on the subgame perfect equilibrium of the induced game, or when we break ties in favor of the outcome that's preferred by the sender, we are effectively looking at the largest equilibrium. And it turns out that this largest equilibrium is easy to characterize in terms of the underlying network. Specifically, if the posterior mean is equal to, let's say, minus k, then if we find a group of agents who have k or more connections within the group, for these agents, the network externalities, the positive network externalities, outweigh the disutility due to the low state. And the largest such set of agents will be the largest set of agents who take action 1. This largest set that I'm describing is referred to as the k-core of the underlying network in network theory. Now, the k-cores are related to the degrees of the agents in the underlying network, but k-core is not the set of all agents who have degree k. Here's an example. So the 0 core of this network is the set of all agents. 1 core is obtained from the 0 core by iteratively removing all agents who have degree less than 1. 2 core is obtained from the 1 core, iteratively removing all agents who have degree less than 1, and so on and so forth. The darkest region that you see inside is the 3 core of the network. You will see that all nodes in this 3 core have 3 or more connections to other agents in the 3 core. But there are agents like this one who has degree 3, but this agent does not belong to the 3 core. So k core is the maximal induced subgraph where each agent has degree k or more. This agent, this node does not belong to the k core of the underlying network. Now, the important takeaway from this slide is the following. For any signal realization, this set of agents who take action 1 will constitute a core of the underlying graph. We can understand the set of agents who jointly take action 1 in terms of the network structure. The groups of agents who jointly take action 1 will correspond to different cores of the underlying network. But this actually gives us a way to recast the design problem of the designer. We can first of all express the designer's payoff as a step function of the posterior mean Hurst signal induces. In particular, the step function has cutoffs at integers minus k. Here, minus k is the cutoff where the group of agents who take action 1 will switch from the k core to the k minus first core. And the reward that the receiver gets when the realization of the state is between minus k and minus k plus 1 is the cardinality of the k core. It's equal to rk. So what I'm describing here through this observation is that we can express the designer's payoff as a step function of the posterior mean Hurst signals induce, and then we can use the framework that I introduced earlier to construct the optimal mechanism of the designer. So here's a recipe. Given a network, compute its different cores, use that to construct the step function, and then apply the convex programming framework to obtain the optimal public signaling structure. Here is a network with, I think it's a Facebook subnetwork with 4,000 nodes or so. I computed the cores of this network, which is a straightforward operation, and I solved the convex program, and using the algorithm that I mentioned earlier, I constructed the optimal public signaling mechanism, which is illustrated on the right. This mechanism exhibits a double interval structure. I associate at most 2 subintervals with with each possible signal realization. And for instance, in these 2 red intervals, I send signal 33, and agents in the 33rd core take action 1. Here in the pink set, I send signal 31, and agents in the 31st core take action 1, and so on and so forth. What you can see in this double interval structure is that there are agents who take action 1 for some states, some low states, some high states, and not in the middle. And it turns out that this is the counterintuitive behavior that's exhibited by the optimal information structure. So the set of states where an agent takes action 1 is not necessarily a subinterval of the states. It is possible that some agents will, at the optimal mechanism, some agents will end up taking action 1 for some high states and low states, and not in the middle. I'm not illustrating it here, but a similar approach is also applicable when there is information only about the degree distribution, when the network is not fully known to the designer. And again, there the key ingredient is the same. By using only the degree distribution in large random networks, the designer can characterize the size of the cores of the network asymptotically. Feeding it into the convex optimization problem that I illustrated earlier, one can obtain asymptotically optimal mechanisms. For details, please see the paper. The second application that I'm going to focus on is a paper of Kimon-Drakopoulos, and this focuses on a completely different environment. Here there's no network, and we think about the seller who offers a product over 2 periods to a unit mass of buyers. We are assuming that the buyers' values are coming from a known distribution, and basically this distribution defines the demand curve, right? If the price for the product is P, then 1 minus GP mass of buyers would like to purchase the product. I'm going to denote this by G bar P, and I have a way of mapping each price to a demand point for the buyers. The uncertainty in this case, the state of the world, if you will, is the inventory is related to the inventory of the seller. Inventory is a priori unknown, and it can be high or low, and it is high with some probability pH and low with the remaining probability. In the high state, the designer, the seller, has enough product to satisfy all the demand in the market. In the low state, on the other hand, she may need to ration, and that's where the friction is coming. Because of the stock out possibility, you may be able to persuade some agents to purchase the product early at a higher price than wait for the end of the horizon. Remember, this is a setting where there are two periods over which the seller is offering the product. What is the seller's or the designer's problem? Well, the seller commits to both an information structure that signals the available inventory and the prices P1 and P2 for periods 1 and 2. So at time 0, I commit to this, and then once the state is realized, once the inventory is realized, I reveal an informative signal to the buyers. Buyers update their posterior about the state and decide whether to buy at all. Maybe they choose not to buy at period 1, or wait until period 2 and buy if the product is still available in period 2. Now, here are the two key results of this paper, which I find super interesting. Number 1, if the seller is restricted to using public signals, that is, if the seller sends the same signal about the inventory to all the buyers in the system, then an optimal mechanism actually involves not revealing any information and setting the prices appropriately. So if you restrict attention to public signals, you don't want to reveal any information. Revealing information doesn't do any good to the designer. On the other hand, the results change drastically if you focus on private signals. In this case, by using private signals, first of all, the designer can substantially improve her payoff, and the mechanism is quite non-trivial, yet intuitive. In particular, the designer identifies two prices, P1 and P2. P1 is the period for the first price, P2 is the period for the second price. If the realization of inventory is QL, the designer recommends, if the inventory is low, the designer recommends agents whose values are above P1 to just purchase in the first period at the high price, and recommends the remaining agents not to purchase. If the inventory is equal to QH, if you're in the high state, then the designer recommends each agent with value above P1 to buy in the first period at the high price with some type-dependent probability. So here, these are independent signals, independent conditional on the state realization being high, and basically I'm sending signals to different high-value buyers, and I am trying to persuade some of them to purchase early on, as opposed to waiting till the second period and purchasing at the low price. Similarly, if the inventory is high, I am recommending all agents, all the buyers whose values are between P1 and P2 to wait until the second period. Now, observe that this is not a trivial mechanism in the sense that I am basically sending randomized signals, and these randomized signals are type dependent, so I may be telling some agent to wait and the other agent not to wait. Still, thanks to the design of this mechanism, thanks to the design of these private signals, the seller can substantially improve her payoff. And really, qualitatively speaking, by discriminating agents with the information that they have access to, the designer can persuade some agents, the high-value agents, to trade at higher prices. And this is what allows the designer to improve her payoff. So this is an interesting result, and it also highlights quite an interesting dichotomy. With public signals, the designer can't really improve the outcome. She finds it optimal to not reveal any information about the inventory. With private signals, there's a lot of room for improvement, and a non-trivial mechanism that allows the designer to discriminate agents leads to substantial revenue improvement. I think this is an interesting result, which also illustrates some neat applications of information design ideas in revenue management. Last application is a paper due to Ramesh Johari, Barlight, and Gabriel Weintraub, where they focus on information design in two-sided markets. So here is the setting. There is a unit mass of buyers and sellers. Sellers' qualities are distributed according to a known distribution, and they belong to a subset of the reals. Buyers' types are distributed according to a different distribution. And if type M buyer purchases the products from a type Q seller at price P, her payoff is type times quality minus the payment made to the seller. And if a type Q seller produces and sells H units of the product at price P, then her payoff is given by her revenue minus a cost term. Here the cost may depend on the quality as well as the quantity that's produced, and in particular it's assumed that the cost is convex in the amount that's produced by the seller. Now, the platform has some partial information about the qualities of the sellers. In particular, there are different quality levels denoted by these sets AK, and the platform does not know exactly the quality of each seller, but it knows to which quality level each seller belongs. So I do not know exactly what the quality of the seller is, but I know that there is a set of sellers whose qualities belong to set A1, there's a set of sellers whose qualities belong to A2, and so on and so forth. So here these sets AK are just a partition of the set of all possible quality levels. The platform chooses information structure, another collection of sets BK. Here each BK is a union of a subset of this collection AL, right? So it may be the case that BK is a union of sets A1 and A2, BK prime is a union of the sets A3 and A4, and so on and so forth. So think about this as the platform starting with a finer partition of the set of possible quality levels and coarsening this information. And BK is this coarsened information structure. And these sets BK are disjoint, and it's important here to note that the union of all these sets BK is not equal to the set of all possible quality levels. Some sellers with certain quality levels may not belong to this union. The platform chooses this information structure as well as the prices for each of these quality levels BK, and the objective of the platform is to maximize the total transaction value. I did not describe to you how the buyers and sellers decide who to trade with, and the paper considers different models of trade. I'm not going to go to the details of this, but here is basically a model that they focus on. The buyers and sellers take the sets and the prices as given, and at equilibrium they choose optimal supply and demand levels, and the market clears. So a solution concept similar to, let's say, a competitive equilibrium concept. The key question here is when are simple information structures optimal? And more formally, the authors focus on the one separating information structures, where the platform bans a group of low-quality sellers from the platform altogether and does not provide any information on the remaining sellers. So it is as if I have a single set, B1, and there are some low-quality buyers who do not belong to B1. Those buyers are removed from the platform, and I do not reveal any information at all about the remaining sellers to the agents in the system. It turns out that these type of simple information structures are optimal when the buyer's value distribution satisfies some constraints. In particular, when this function FB, the buyer type distribution FB, evaluated by M times M, if this function is convex, and if some additional technical conditions hold, then one separating information structure is optimal. And they, along the way, provide a nice reformulation of the problem of the platform over menus of price and expected quality pairs. Now, I want to highlight that this is an information design problem in a different environment, in a different setting, in the context of platforms. It's a natural problem, and it's important to study the optimality of simple information structures, which the authors deliver on. It also is an information design problem which has a different flavor than what we have been focusing on so far. So far, we focused on settings where there's an underlying state of the world, which was one-dimensional. It was a subset of the reals, let's say, and the designer was sending signals about that state to the receivers in the system. Here, that's not quite the case. We have uncertainty about some of the agents in the system, our sellers, and it is not commonly known the qualities of each of the sellers, and the platform reveals information about the quality level that each seller belongs to. So we do not have a single state of the world which is independent of our receivers and whatnot. Really, the information that we are revealing is about some of the agents in the system. So in that sense, it is an information design problem with a different flavor, but similar ideas still are in play, and it is possible to explore the optimal information structures in this context as well. So let me conclude and highlight some future directions. The recent literature has explored many other interesting information design questions that I haven't had a chance to discuss in this tutorial. There are papers, for instance, that focus on settings with informational spillovers. Imagine a setting where we have many receivers. The designer can send informative signals to some of these agents, and the agents talk to each other, and the information can spill over from one agent to the other. in a setting where there are such informational spillovers, how can one design optimal information structures? That's one question that started receiving attention in the recent literature, which I find super interesting. There are problems, there are questions related to privately informed receivers. So far, I assume that the receivers do not have any private information. In settings where they have private information, the designer may need to come up with information structures that take into account the private information that the receivers may have. How should the designer take into account this information? That's another interesting question that few papers are trying to answer. How can we come up with robust information structures? How can we think about designing information in a dynamic way? These are some other interesting questions. So these are all recent research questions in the area that are pointing at different directions, and I think there's a lot of work to be done in each of these directions. In addition, I think for the operations community, there's a ton of opportunity in terms of thinking about how different operations can use information as a lever to induce a desired outcome. I think there will be interesting applications of information design tools to service operations, to ride-sharing platforms, to transportation networks, to e-commerce platforms. In all of these settings, the operation or the platform has some information about the underlying system and can send informative signals to the agents in the system to change their behavior and to induce a desired outcome. How to do that in the best possible way, taking into account various operational considerations, is something that the community could work on. We are already seeing some papers related to some of these questions, and I think there is room for many more interesting works. Also, a question that I find super interesting is the interplay between information and other levers such as pricing and admission control. In some of these papers, some of the papers that we discussed today, we already saw that the authors were thinking about using pricing and information and optimizing both of them jointly. Broadly speaking, it is not clear when information and other operational levers complement each other and when one may be a substitute for the other. And I think it's important to provide a broader understanding of the interplay between different operational levers and information. So I'm going to stop here. As you noticed, there are many interesting questions, and I hope that this tutorial was inspiring for some of you. I hope that in upcoming Informs conferences, we'll see many more applications of information design to different operational settings. Thank you for your attention.